Hi everyone, and welcome to the Activity 6 notes. Today we are going to talk about transformations and even and odd functions. What you see in front of you is a bunch of different parent functions. Now these aren't all the parent function graphs, but these are some typical ones. And a reminder, when we think about domain, that is dealing with your x values, range deals with your y values. And for a lot of these graphs, for instance, this linear function, no matter what x value we plug in from negative infinity to positive infinity, all real numbers, our graph is going to give us an output value that is all real numbers as well. And this is, pretty standard for not only that graph, but also our cubic function as well. Like anything we plug in x value wise is going to give us a y value output. There are no limitations on either. Some of these graphs, however, are going to have some limitations on our output values. For instance, we can plug in any x value we want to the absolute value graph. However, our y values are only going to be numbers greater than or equal to 0, or sometimes we would write that with interval notation as 0 to infinity. Same idea with the quadratic functions. We can plug in any x value we want from negative infinity to positive infinity. However, our y values will also be limited to being greater than or equal to 0. On the other side, our square root functions, there are some limitations as well to our x values because we only want x values that are greater than or equal to 0. If you try to take the square root of a negative number, you don't get an output value. So we would say the x's are from 0 to infinity. We include 0 though. That also means our y values are limited. Notice we don't have any y values on the left-hand side of the graph, so our y values are only going to be greater than or equal to 0 as well. Exponential functions, we could plug in any x value we want. However, we're going to get a limitation to just have y values greater than 0. Notice this time we are using parentheses, not brackets, not or equals to, because we're going to get infinitely close to 0, but never actually touch it. On our last one are limitations for domain on this one. X is not going to equal 0 this time. It could be any other real number, but we are not going to have any x values because of that vertical asymptote at 0. So we would say this is from negative infinity to 0, or from 0 to infinity, but we don't include the 0. Same idea for our y values. We have this break in our graph with the y values. So our y values are also going to be anything except 0 because of that horizontal asymptote. So again, from negative infinity to 0, we're okay, or 0 to infinity, but we're not going to include 0. Now, we can also use then transformations to shift these different parent functions around. And so we're going to see for an k value on the outside of our function, what this will do is shift our graph either up if it's plus k units, or down if it's minus k units, right? So we go up or down based on that shift there. We also have a horizontal shift. Now notice this is going to be inside of the parentheses, and these are kind of opposite of how they look. What do we mean by that? Well, the plus h is going to shift our graph to the left k units versus the minus, which is actually going to shift our graph to the right k units. So again, be careful because it's almost opposite of how you would think based on the plus or minus. We also have the idea of a reflection. Now think about a point, for instance, right here. If you are negating the y value, you are actually going to reflect this so that it goes down, right, over that x-axis. Versus if we have this point and we change the x value on the inside, we end up reflecting it over our y-axis. And notice that's what's happening is because we are changing the y value on the first one, it flips it over that x-axis. Change the x value in the second one, it reflects it over that y-axis. We also have the idea of vertical stretches and compression. So this is going to happen when we have a figure on the outside and it's going to affect our y values. It's going to get taller versus a value that is less than 1 that's going to compress or shrink our graph. It affects the y values as well, but it makes our graph shorter. When our value is on the inside, and be careful on this one, it's bigger than 1, this is actually going to be a compression by that factor. So it's going to affect our x value. It's going to make our graph skinnier. And if that is a fractional value on the inside, it's going to affect the x value. It's going to actually make it wider on that. So you're going to definitely want to make sure you get these jotted down, and we see kind of again in a color. More than one of these can be happening at once as well to be able to see this. Now, so if we look then at the next page, we see a bunch of different examples for actually using these. So again, each piece of this is going to change each of our functions. So notice on this first one, we have this negative in front of the 2. And what this is causing is that change in our y values, aka reflection over the x-axis. This 2 out front is going to create a vertical stretch by 2, all right, by that factor. The +1 is going to move our graph left 1 unit. The +3 is going to move our graph up 3 units. In our next example, we again have that negative out front. So again, that is creating for us a reflection over the x-axis. This time, our 2 is on the inside. So this is actually going to be a horizontal shrink or compression. And this time, be careful because this is going to act oppositely. Even though it's a number bigger than 1, remember that's the compression. So really what's happening is it's compressing it by a half. And then our last piece, this -1, is moving our graph to the right 1 unit. Down below in our next examples, okay, we see a couple more. This one has a 1/3 out front. So this is our vertical, this time compression, because it is less than 1. And again, it's happening by a third. This time our negative is not on the outside. So it's a reflection, but it's changing our x values for a reflection over our y-axis. And then we have this +1/2. That's going to shift our graph up half a unit. And then last but not least, for our final one, we have this negative out front again. So we're back to having a reflection over the y-axis. Oh, excuse me, x-axis, because we're changing the y values. Okay? And then the 1/2 this time is on the inside of our graph. So this is going to be a horizontal stretch because it's less than 1/2. So we're going to stretch it out by 2, because again, it's kind of the opposite. And then last but not least, we see this -7 means we are moving our graph down 7 units. All right, next, if we look at is a function even versus odd? Well, again, going back to our parent functions, if we check this out, for instance, anything that has symmetry to our y-axis. So the absolute value function we can fold over and it maps on itself. Or the quadratic function we can fold over and it maps on itself. These are going to be examples of our even functions with that y-axis symmetry. On the other hand, if we can take our function, for instance, if we look at the cubic function here, and if we take this graph and we are able to take it, and if we turn it upside down, and it looks exactly the same as the original, like this one does, then this is what we call an odd function. So it's what we say it has symmetry to the origin when this happens, and that's our odd function. Now keep in mind, a function could be neither if it does not have symmetry to either one. We can also look at these algebraically. So basically what you would do is you would plug in a negative x. If it comes back looking like the original, it's even. If it comes back looking like the original function but negated, it is odd. So essentially to do this step, you would just need to multiply the original function by -1 check that out. Flips the signs of the original. So if we look at these first couple examples, okay, we could test out, are these even or odd, by looking at these graphs and testing out that symmetry. So if we look at this, we have x to the 6th power minus 2x to the 2nd power, and then plus 3. And if we look at this graph, what we notice is we can, in fact, fold this over that y-axis, and it maps onto itself, so that we would say this is an even function because of the symmetry to the y-axis. Our next example, if we look at part B, is we can take -2 and then x to the 5th power plus x cubed and then minus 9x, and we get this graph right here. And what happens on this one is if we can take this graph and if we take this and we are able to flip it upside down and it looks the exact same as the original, we know it's odd. Well, if we compare this graph to its original graph, those look identical, right? So we could say that this one is an odd function because it has symmetry to the origin. Last example we have is x to the 4th, and then, we have x to the 4th minus 2x to the 3rd power, and then plus 5. And we see on this one that our graph does not have symmetry to that y-axis. If we take this graph and we try to flip it upside down and compare it to the original, these definitely don't look the same. This is now like a downward facing, does not match our original whatsoever on that. So this is going to be neither even nor odd. So we have a couple more of these, just looking graphically. Again, this one is going to be an example of an even function because of that symmetry to the y-axis. This next one, if we flip it upside down, this is going to be odd because of the symmetry to the origin. And then last but not least, if we try to take the symmetry on this one, we're going to notice that it does not look like it has any symmetry to the y-axis. It's not even. If we take this picture, flip it upside down, it is not the exact same as the original, right? We have a point here, we have a point here. Those are not the same location. So this is not the exact same as the original. So we would say that this is neither. There are also 3 examples for you to try to finish this out. And then thanks everyone for watching. We'll work more in class.